So we have the equation 7.69. So this is equation 7.69, which is given as transition probability. Transition probability between two states is given by this expression 1 by h bar. 1 by h bar is given by this equation. So as I said, t tends to infinity. That means omega tends to 0. Okay. So we have the phase factor. We can write the phase factor exactly like this. And this f of omega ml is proportional to delta function, because at t tends to infinity, when omega tends to 0, em is very closer to el, we have a delta function. Okay, the contribution will be more only around the central peak of the probability distribution of electrons. Okay, now we will consider the f of omega ml as this term, phase factor. As usual, we have done just now. Omega, you just keep it as omega ml t by 2, which is equal to x. Your omega ml equals, cross multiplying, you will have do 2x by t, d omega equals 2 by t dx. Okay, you substitute here in this in the above expression. So we have 4 sine squared x by, instead of this you just substitute 4x squared by t squared, and you have d omega, which is nothing but 2 divided by t dx. T will cancel. Okay, 4 and 4 will get cancelled. You have 2t multiplied by this factor, and this standard integral, the value will be pi. You just substitute, you will have 2t pi. So this is your pi. 2t multiplied by will give you 2t pi. Okay, as I said just now, the central peak is proportional to your delta function. Okay, so we can write the probability which is equal to 1 by h bar square, your the square of the perturbing field multiplied with this answer multiplied by the delta function. So del of omega ml. Del of omega ml equals del em minus el by h bar. So omega equals e by h bar. So omega ml is nothing but em minus el by h bar. The property of delta function is given as h bar del em minus el. So we are going to substitute here. Okay, instead of this we are going to substitute h bar del em minus el in that expression. Okay. Now of course we will have to bring this t to left hand side. That will give us transition probability per unit time, which is nothing but your WML, which is given as this expression. Okay. Now as I said that stationary states will go to higher states when the perturbation will occur. At the time we will have continuum energy states. Correct. A lot of levels will be there in the excited states. So this can be replaced with summation. So this can be replaced with summation. Okay. So we will have a lot of levels in the excited states, not only single level. So summation over in the final state, and this can be replaced with density of states, number of states of the final state between E and E plus D. So rho of EM denotes the density of final states. Then the above equation becomes exactly like this. So which is nothing but Fermi's Golden rule. So in two ways we have derived Fermi's Golden rule. One is without delta function, another one is with delta function. Whatever way which is simpler, you just take. In some other book you may find without delta function, in some other books you may find with delta function. Okay, both the results will give you the same result. Both the answers are correct. Okay, so your transition probability between two states per unit time, which is nothing but Fermi's Golden rule, which is equal to 2 pi by h bar multiplied by the square of the perturbing field multiplied by the density of states. So this result is a theoretical result which is exactly resembles with the experimental result. So that's why it is termed as Fermi's Golden rule. Okay, the above formula, equation 7.77, has wider applications not only in quantum mechanics but also in atomic, nuclear physics, solid state physics, okay, material science, okay, and also in chemistry. The first order perturbation theory expression involving a matrix element squared and the density of states is very common in the calculation of chemical rate process. So in chemistry also it is used. This formula has wider applications in quantum physics. The theory of scattering, which we studied in the last unit, scattering can also be explained with the help of this formula. The matrix element, which is nothing but this is your matrix element, which is invariant across the final states. Okay, not only in physics but also this is used in life too, as I said. Okay, that's why it is termed as Golden, Fermi's Golden rule. The theory of scattering can be explained with the help of this equation, which is known as Fermi Golden. Okay, so I have repeated. This equation states that in order to calculate the transition rate, all we have to do is multiply the square modulus of the perturbing field term, which is nothing but perturbation matrix element, between the two states by the density of states at the transition. Okay, we are going to square this one, multiply by this will give you transition probability per unit time. So it says the transition probability per unit time is non-zero only between continuum states of same energy in the final states. First one, and second one is it is proportional to square of the perturbing field, okay, matrix element of the perturbation connecting the states, and third one is it is proportional to the density of final states. The intensity of spectral lines, so this is what I said about Niels Bohr's contribution. Niels Bohr contributed with a lot of data about the hydrogen atom. The intensity of spectral lines are proportional to these transition probabilities. This is contribution given by Werner Heisenberg. This contribution is given by Niels Bohr. So both match with each other. So one is experimental side, another one is theoretical side. Okay, probabilities as they depend on the rate of transfer of energy between electromagnetic field and the system. So light in touch with the matter. So very famous and good example. So now we will try to solve one problem. Problem 1. Okay, a particle which is initially t equal to 0 in the ground state of infinite 1D box. So a particle is confined in the 1D box. With the walls, the boundary condition is x equal to 0 and x equal to L, which is subjected for t lies between 0 and infinity. To a perturbation, the expression for perturbation is given by this x squared e power minus t by tau. We are going to calculate the first order probability of finding the particle in the first excited state for t greater than or equal to 0. So we are going to find out the probability. Okay, the probability of finding the particle. Okay, so for a particle in an infinite potential, we know the energy expression is given by this. So we studied in the quantum mechanics 1. Okay, in infinite box as well in finite box, we studied this n squared pi squared h bar squared. Don't forget this is h bar squared. So as I said, incompatible with the screen, h bar is missing. Okay, so this is h bar squared divided by 2m L squared, and the corresponding wave function for the 1D box is given by this. With the ground state n equal to 1, first excited state n equal to 2. So calculate the first order probability. So we are going to find out the transition rate between ground state and the first excited state. So that's why it termed as n equals 1 and n equals 2. So now we are going to use equation 2.8. So equation 2.8 is given like this. Okay, this is your equation 7.28. So which is nothing but your amplitude. So this is your amplitude in the first order correction in the time dependent perturbation theory. Okay, now squaring will give you the total probability, transition probability. So this is your amplitude. Squaring of amplitude will give you total probability, the transition probability. So just to square the term. So we know that the expression for h of t is given as x squared e power minus t by t. Just to substitute here. Just to substitute. And we are going to separate this one into two terms. One is x squared, another term will be e power minus t by t. One is x term, another one is t term. We are going to separate. So this is a d psi by dx, correct? D psi by dx. So we are going to separate in terms of x squared. We are going to separate this term in terms of t. I repeat, see here we have a perturbing field is given as x term and t term. X squared e power minus t by t, and the psi depends on x here. So that's why we have taken this side. So we are going to separate. Separately we are going to integrate. So we are going to integrate this and we are going to integrate this. Separately we are going to do. Okay. So say x squared sandwiched between your psi m and psi l mod squared, and this term will be integration 0 to t e power I omega ml t e power minus t by t d term. So now we are going to separately we can do. So we are going to do separately and we are going to multiply, we will get the final answer, transition probability. So that's the idea. First we will go with, as I said, we will go with separation. Okay, separation of integral. So 0 to L, L is the side of the wall, okay, length of the wall. So 0 to L, psi m x squared psi L dx. Okay, so we know that psi n is given by this. So psi l is given by this. Your psi m is the first excited state, correct? First excited state. So your n pi x will become 2 pi x. N equals 1 for this, n equal to 2 for this excited state. I repeat, x squared psi m star psi n. Your psi n is given by this when n equals 1. Psi m is the first excited state. So your n will become 2. So that's why it is written as 2 pi x by n. Is it okay? And root 2 by L multiplied by root 2 by L will give you 2 pi L. So 2 pi L integration x squared and this term. So this is standard integral. X squared sin A sin B will give you standard integral. The answer is minus 16 L squared divided by 9 pi squared. Okay, this is standard integral. Squaring. So we have to square, correct? For everything we have to square, mod square. So taking the square will give you 16 L squared divided by 9 pi squared whole square. So we have found out the first one, answer for the first one. Okay, answer for the first one. And we will go for the second one, t term. First one is we have finished x term. Now we are going to find out in terms of t. So this we are going to integrate this. When you are going to integrate, this will become integrating 0 to t, this will become e power minus 1 by tau minus I omega ml divided by t divided by this term minus 1 by tau minus I omega ml. Now we have to substitute the limit 0 to t. When you are going to substitute the upper limit, that will give you t. When you are going to substitute the lower limit, that will give you e power 0, answer will be 1. So minus 1 divided by this term. This is mod square. Okay, this is mod square. So we can take this minus out. This will become plus. Is it okay? This is mod square. So that will become plus sign. Now you will have to take the complex conjugate and multiply. E power minus x minus 1 multiplied by e power minus x minus 1. Two factors will be there. So we are going to multiply with the complex conjugate. So for the numerator, we are going to take the separate, we have separated the term and multiplying with the complex conjugate, this will become e power minus t by tau. So this will become minus minus plus. So this will become minus. Is it okay? So we are going to have e power minus t by tau. So this will become one is minus, another one is plus. Okay, is it okay? Divided by your numerator will be 1 by tau minus I omega ml multiplied by 1 by tau plus I omega ml. We will have to take the complex conjugate. Taking the complex conjugate will give you this factor. I repeat, come on. You have e power minus 1 by tau multiplied by e power plus I omega ml. Correct? I omega ml t. I have written here. Take the complex conjugate, you will get this. That's all. Now you are going to multiply this term with this term. When you are going to multiply with this term to this term, answer will be, first we will go with 1. Minus 1 multiplied by minus 1 will give you plus 1. When you are going to multiply this term with this one will be 1 and this one will be e power minus 2t by pi. And the rest of the term, this term multiplied by minus 1 multiplied this term will be this term, these two terms. Is it okay? I repeat, minus 1 multiplied by minus 1 will give you plus 1. This multiplied by will give you this one will be 1. E power minus t by tau, e power minus t by tau will give you e power minus 2t by tau. And rest of the term, this multiplied by with minus 1 multiplied this term will be these two terms. So as usual, I can pull e power minus t by tau out. So I can obtain this expression. Multiplying and dividing by 2 will give you this expression in the numerator. This can be replaced with cos omega mlt, which we have already seen this type of results earlier. So that will be 1 plus e power 2t by tau minus 2e minus t by tau cos omega mlt divided by, when you are going to multiply these two will give you plus omega square ml plus 1 by tau square. Okay. So now we are going to apply the limit. So when you are going to apply the limit, t tends to infinity. That means for the central peak omega tends to 0. So the numerator, that is the numerator in that expression, that will become 1. Denominator alone will get the answer. So numerator will become 1 and denominator will be omega squared ml plus 1 by tau squared to the power minus 1. We know that we are going to substitute for omega ml. So we know that omega 21 is given as E2 minus E1 by h bar. We know already. That is omega ml equals Em minus El divided by h bar. We know already. So Em minus El divided by h bar equals E2, the first excited state, which is nothing but your 2 square, n square. We know the formula, which is n square pi square h bar square divided by 2ml square. So this will become 2 square. So 2 square I have written. For the ground state, this will become 1 square. So 2 square minus 1 square will give you 3 square, 4 minus 1. So 3 pi square h bar divided by 2ml square. So we know that omega ml is given as this expression. Squaring will give you 9 pi to the power 4 h bar square divided by 4ml to the power 4 plus 1 by tau square to the power minus 1. Okay, so we have found out the second integrals expression. The first one is given as this. So multiplying these two will give you your total probability. And of course 1 h bar is outside. 1 h bar square is outside. So we have 1 h bar square. We have found out the expression for this, which is given as this. We have found out the expression for this, which is given as this. You multiply these two will give you the final answer. Okay. So now I have taken this h bar square inside. You just see here 16 L square divided by 9 pi square. This h bar I have taken inside. So it becomes h bar because this is whole square. So h bar whole square. This is the contribution from this. This is a contribution from this. So this will give you total probability between two states, your ground state and the first excited state, 1 and 2. So this is the answer. Total probability between two states in a box is given as this expression. Okay. So thank you students. We will stop today. We will see in the next class. Bye.